Good afternoon, everyone. I'm Arnab Sarkar from IIT-Kanpur. I'm working with Dr. Saikat Ghosh here. So today I will talk about cooling of a mechanical mode. As you can see this picture, so a mechanical mode of a single layer graphene membrane, and that experiment is done at room temperature, and through the technique I will explain. As I said, this is the same image of the sample we are working on. So it's a single layer graphene membrane with a 20 micron diameter. This black circle is the graphene membrane, and this gray area, this is a much larger than this, so it has a larger area. So this is a silicon nitride surface. Now, so this whole sample, this is like a mechanical resonator. So it's like a tabla. Like if you so if there is some forcing, it will oscillate along the z direction, so out of the plane, right? And this silicon nitride surface also is a resonator, but because this is a thin, like low mass oscillator with respect to the silicon nitride, so the silicon nitride will have much smaller displacement. Like that, it is like 10 to the power 4, like mass wise, it's 10 to the power 4 times heavier than graphene. So we put this sample in a capacitive arrangement. So there is a lower gating chip, and this is our sample. We can put DC voltage, AC voltage to actuate this electrically. So I will come back to this later in detail. And this whole arrangement is kept inside a vacuum chamber. It's a rough vacuum, like 10 milliliter kind of, and then it's kept on a stage. So we can move it like the whole this vacuum chamber along 3 direction XYZ. Now we focus a confocal like microscope, and we use a ECDL laser to send a probe light, which is very small in intensity, to just probe the system. It's 200, 200 microwatt power. Like it will not disturb the system. So and this reflected light we detect using spectrum analyzer or imaging. We can do imaging and all other things. You see the other arm, we use a piezo, and when we use this other arm also, it becomes a Michelson interferometer. So then this arm, and using this feedback through like the noise feedback, this signal becomes very stable. So we detect the signal. If we look at the spectrum, so the spectrum looks like this. So these are the fundamental. So now this circular drum, this will give us like Bessel modes, right? So these are this is the fundamental mode of a Bessel, the fundamental Bessel mode, and then the higher order modes are there also. And you see it has amplitude which is in picometer. So so because this is a very thin membrane, only because of thermal fluctuation, it will have Brownian motion. Due to that Brownian motion, so we will see this Lorentzian kind of peak, and if we feed this, we can extract. So these are thermal phonons. So area under the curve will give us the number of phonons for this particular mode. So now this each of the mode we can treat as a independent harmonic oscillator, right? So this is the, so I want to stress this, that this is only like Brownian motion. We are not driving it, like just thermal fluctuation will giving us this amplitude. Now for the silicon nitride, that is not the case, because it is heavier, I said earlier, and it is bigger also. So to see the peaks, we have to drive the system. When we drive the system, like with a weak amplitude, we see very densely packed, because this is this area is very high. So like large area. So the around that same frequency, 3-4 megahertz, where we found the fundamental frequency of graphene, around that frequency, actually the silicon nitride will have very densely packed modes. And we know like quality factor of silicon nitride is higher So these are the modes. So the fundamental will be much below, like around kilohertz or something. So yeah, so now we have understood the mechanical modes of graphene, mechanical modes of silicon nitride, and then let me explain this actuation process. We can, so I said earlier, we have this electrical connection. We can put a DC gate voltage. If we put a DC gate voltage, because this is a capacitive arrangement, so you increase this gate voltage, tension increases, the fundamental frequency. So this is the gate voltage I'm talking about, this DC gate voltage. And if you look at the spectrum, like on Fourier transform spectrum or like spectrum analyzer, you will see that this there is a dispersion curve. So the fundamental frequency will shift because tension is changing. So this is the fundamental frequency. And in fact, you put AC voltage to modulate this signal. Now I will come to this AC voltage later, so it will be there. So now if we zoom in little more, so what we will see that as I told earlier, this silicon nitride is a heavy mass oscillator. So with this tension, silicon nitride frequency will not change. So they will remain almost constant. And because our graphene mode is shifting, so we will see that it will interact with different silicon nitride modes on resonance, and we will see avoided level crossing. So it's like this black dotted curve. It's like the graphene mode, and then you have a strong silicon nitride, which we will not be able to see because this is below noise floor. And when they are hybridized, so this detuning will see us this avoided level crossing, and we will see two hybrid peaks. So this thing will come again in later when I will explain our experimental schemes. So yeah. So now, so what we can do with this? Yeah. So this is a work done by Rajan Singh, my senior. Now he's in Weizmann. So it's published in 2018. So what we have a heavy mass oscillator, which has small displacement, and we have a low mass oscillator. So the idea is simple. If you have a heavy mass oscillator, attach a low mass oscillator with it, put a little force on the heavy mass oscillator, what will happen? It will move, but we will not be able to see it. But that small displacement will give a bigger displacement to the low mass oscillator, so that will oscillate. So we do the same thing. So we thermally excite, like we put a laser, we excite this optically, like we put some force, the graphene, on the silicon surface. So the small force that is reflected on the graphene surface, and it's amplified. Right? There is a huge amplification, and if we check the what is the sensitivity of our detection, that is 5.5 femtometer. So yeah, so this is around like like it's smaller than an atom. So we can measure very small displacement, like smaller than an atom. And then, like, can we improve this? Yeah, we can, because again, so that one problem is there. When you are saying sensitivity, there is signal, there is noise, and because this is low mass oscillator, signal will be amplified and noise also, right? So now when there is no amplification, so this is the electronic noise we are talking, the electronic thermal noise we are talking about, the total noise. And then after the gain, you see this noise is also increased. So noise is also amplified. So somehow if we can reduce this noise, that will increase our sensitivity. And then the parametric drive is well known. So if we do drive this system parametrically, and we look at the quadrature, like this is like, if you look at like X quadrature and Y quadrature plot, the noise will be like, if you don't do parametric drive, that will be a circular distribution, like both the quadrature same, but after the driving, it will distribute like that. Squeezing will happen, and our detection, our sensitivity goes to 3.8 femtometer. And so few things, yeah. So there is a limit. We cannot go like this squeezing. We cannot like squeeze it infinitely. the limit is 6 dB. So now again we ask the same question. Okay, now we have reached 3.8 femtometer. Can we reduce this temperature to increase, like this thermal distribution, the noise distribution that is due to temperature, right? So if we reduce the temperature, then hopefully that noise will reduce and our sensitivity will increase more. Okay, so what to do? We can do many things. Like there are many processes. You can put it in a refrigerator or do sideband cooling or do other cooling methods that exist in like sideband cooling also used to cool down trapped atoms, and like many atomic system we have seen different cooling methods. So we propose a different cooling scheme where we just modulate its frequency. You remember this thermal peak, so there are thermal phonons. So our target is to reduce its temperature. So we are not targeting to reduce I mean, we are not putting it in refrigerator. We are trying to cool down this particular mode. To do that, we are putting a AC signal. I told you, like we can put DC signal, we can put AC signal. So we are putting an AC signal. Like look at the frequency. So our graphene has a frequency of megahertz, and we are putting a kilohertz frequency. And so if our response signal is cos omega t, this is the frequency, this is the amplitude, and then putting a frequency modulation. So the frequency will be modulated by this h will be our modulation depth, and omega p our modulation frequency. This omega p will be kilohertz, right? Kilohertz, and omega 0 is around megahertz, and we will see that amplitude of the modes, like there will be side modes, and the amplitude will follow a Bessel's function, like Bessel's function of first kind, and the order will be like the central one will be 0th order, this one will be first order, second order, like that. So this Lorentzian peak, this has some height, like some number of phonons are there, and then at a certain H value, at a certain modulation depth, the amplitude has gone down. Like this is not experimental data. So this is our scheme. So and then amplitude is distributed to the sides. And the amplitude, if we try to if we look at the amplitude, how they should change, like the 0th order should go down here, and around this point we expect it's totally 0, and the others like energy will be shifted to the side modes. We experimentally check that, and this is our thermal peak I was talking about, like now. And then this rate curve, you will see that central peak is going down, the amplitude is going down, and we are seeing there are side peaks coming up. Yeah. So okay. Now, yeah. So now we are looking at the spectrum. So this is the fundamental mode of graphene, and we increase the modulation depth. So it's clear that this yellow line is the higher amplitude and red one is lower. The central peak is going down and the side modes are coming up. So this is the cross sections. You see that area under the curve is going down. From a fitting of Lorentzian, we immediately can calculate the temperature, and like it's a room temperature experiment. So our T0 will be 300 Kelvin, and the temperature. So this blue data, this is the extracted data from this spectrum, and we feed this Bessel's function of first kind, 0th order. It's fitting well, and the red one is the extrapolated curve. So what is happening here? So we are limited by this 51 Kelvin. We can reach up to 51 Kelvin, and we cannot go below that because there is a noise floor. So when this system is hitting the noise floor, so we cannot do like more than that because there's a noise floor, and then we see some different thing. So I will come back to this. So now, like till now, so this is evident that yeah, we can, using this frequency modulation technique, we can cool down a mechanical mode, and this temperature is pretty like I mean at room temperature, I mean, the striking thing is that if we can somehow go there, if we can shift this limit, very soon we can reach to like close to like ratio will be very close to 0. But and if we look at the thermal occupancy, so the phononic occupancy, how many phonons are there, so that this function, and then you will see that it is around 10 to the power 7 or less than 10 to the power 7. But again, the magic happens here. If you can somehow shift this limit, shift this barrier, you can go to single phonon limit immediately, very soon, just away. Okay, so this is promising, and then I'm telling that this is better than resolved sideband cooling, because we have seen that cooling rate, this cooling rate is increasing with modulation depth, which is not in the case of resolved sideband cooling. There you will see a flat line. I mean, the cooling rate is constant with modulation depth. Okay, so till now, so we have established that we can cool down a graphene membrane, and then I told you that this graphene interacts with silicon nitride. So now the question is that, okay, if you take a silicon nitride membrane, you cannot cool it down because it is already below noise floor. But if it is interacting with the silicon nitride and it is giving you hybrid modes, can you cool them down? That is the question we are asking. And yes, we can. And it depends. Is it efficient, and where it is efficient? We change the frequency, we change this modulation frequency, and we see around 17 kilohertz, which is the frequency difference between these two hybrid modes. Around that frequency, this is most efficient. And then if we fix that frequency and we change the modulation depth, we see that these two peaks, the hybrid two peaks, its amplitudes are going down and the side peaks are coming up. Again, we extract temperature. Again, we extract temperature, and we have seen that this temperature is going up to 90 Kelvin, and again we have this thermal noise floor that is stopping us. Okay, and we can do numerics using this. This is representing a graphene resonator. This is representing a silicon nitride resonator, and there is this epsilon p is the modulation depth, omega p is the modulation frequency. So we numerically see the same thing. Okay, so we have established that we can cool down the hybrid system also, and then we go back to our that question, what happens here? So we know this limit is a thermal like this is the noise floor, and if we do more, like if we keep increasing that modulation depth, what happens? We have seen that actually, so we are still analyzing this data, trying to understand more. We have seen that this threshold value that I'm talking about, it's actually threshold value which depends on the modulation frequency. If we change modulation frequency, you can see here this is the thermal peak and the side modes are coming up, and then after a certain threshold value, it goes into a regime where our spectrum will be like the continuum. It's almost a continuum. Its amplitude is much higher. This is log scale, intensity log scale, so it's much higher. So what is happening? Look at the cross section. So the cross section is telling us that there are like generation of multi peaks, and then it's doubled, and then again in between we are getting peaks. So probably we are seeing some chaotic response which is coming through period doubling. So this is our numerics, and our numerics also matches with, like, not really matching. There is some frequency shifts. We are still studying this, why this is happening, or whether there should be like it is over parameterized or not, this numerics, that I need to check. Okay, so yeah, I think I am almost done. What is happening? What is happening? It's not changing. Okay, okay, sorry. Yeah, so now, so this is a cross section. This is numerical result. So yeah, this whole spectrum is going up also, and then there is some limit there. It's going to 0. You can see for different frequencies. I think these notations are wrong. For different frequencies, this spectrum is changing like the other graph I showed. I think so. That's it. So I mean, let me conclude it. So this we can cool down the mode of a low mass oscillator, and at low temperature. So like if it is not limited by this noise floor, we can in principle reach to single quantum limit. But there will be like questions. I mean, there will be more problems. And then this technique is not limited by conditions like you don't need any resolve, like you don't need to resolve anything because like there is no other mode. And then this cooling rate is better, which I told you. And yeah, we can cool down hybrid modes also. So now there is another setup in our lab, which is a cold atom rubidium 87. And Pratik Adhikari is here. He will talk about this. And our near future goal is to interface this to setup and look at the signal from here to here or here to here. And yeah, that's it. So this is my lab members, Saikat, Ghosh, and these 3 people, they are working on this cold atom setup. These 3 people are working on this graphene setup, and very soon they will work together, everyone. Okay, thank you. Questions?
Let's first thank Arnab. Then Prasanna has a question.
So I just had a little bit of a question about the cooling business. So when you are looking at this modulation based cooling, at least from what I saw of the classical description, so if I understand correctly, what you're doing is you're sort of dressing your original phonon mode with the drive modes, and you're sort of keeping the driving on while you're doing your sort of probe measurement to see how many phonons are there. So I was just wondering, because one of the things with, let's say, any kind of sideband cooling or any proper method to cool is that when you turn off the cooling lasers and then do the probe, you should actually see a difference between the phonons you started off and phonons you have. Would you really see this? Because in my head, it's like basically you've moved basically the frequency of your oscillator away. And so even though the environment has energy, there is no system modes to occupy for the environment. Of course, it's going to go to 0.
Yeah, so yeah, that is a very good point. Actually, that is, so it's not that like resolve sideband cooling, we are pumping out phonons from the system to reservoir. So it's the phonons are there, you turn off the modulation, the phonons. So it's a dynamic, like stable state, dynamically stable. Yeah.
Professor Dattagupta has a question online, and then we'll go to Arijit.
Yeah.
Actually, this question is regarding your level crossing and avoided crossing, what you are showing. You are looking at the real part of the frequency. Did you look at the lifetimes? Do you have any lifetime splitting before this splitting of the real part?
So, sorry, sir, I could not hear.
So you are looking at this level crossing and the avoided crossing phenomenon.
Yeah.
When silicon nitride mode is interacting with the graphene mode, right? And
Yeah.
then you're looking at only the real part of the frequency, how the frequency split and the normal mode splitting you are showing. So usually, generally, there is a splitting of the lifetimes. Did you study the weights of these resonances, the split modes and this original resonance, how they evolve as you change the frequency? Did you study that?
No, actually, we have not studied that.
So this is the first part of the question. Second question is about, can you have any analog of this vacuum Ravi splitting? That means silicon nitride film, you don't try. You look at the vacuum modes of the silicon nitride interacting with the graphene mode. Do you still have splitting? Can you still get this splitting? I'm talking about analog of vacuum Ravi splitting.
No, I think no. Vacuum Ravi splitting kind of no.
Okay, thanks. Maybe Saikat can shed some light. Saikat?
Yeah, so I think like the vacuum Rabi splitting is when coupling through a dipole Hamilton to the electromagnetic field. These are just two mechanical modes coupling, basically. So it's an interesting question that at some point, if in reality any group or our group can at some point reach to few quantas, then one might start seeing that plus half h bar omega effect from the phonons. But not, yeah, so in that might actually, that those kind of couplings might give us splitting, but I don't know whether one would call that vacuum splitting, I don't know.
You're looking at the vacuum modes, the phonon modes, so that's, you are looking at the coupling with the graphene mode. So that's, I would say that would be the exact analog.
Yeah, the only difference I was trying to make is that it's basically like, there's no continuum it's coupling to a one specific mode, but otherwise I guess the physics is similar, yeah.
Okay, yeah, okay.
We go to next question.
But lifetimes you don't want to study. Lifetimes, whether there is a splitting of the lifetimes and how they behave.
Yeah, regarding the lifetime, this work was actually like a earlier person. So, so basically, you know, like we have been looking at the lifetimes, also the quality factors, and even from this avoided level crossing from the splitting and so on, one can estimate. And we also have lock-in measurements of direct lifetime measurements. So kind of those quadrature ones are real-time measurements that he was showing on squeezing, and they are actually like from there also one can estimate, or one can actually directly measure the ring down, and we have done those measurements, and then they correspond.
Okay, thank you.
Okay. Arijit?
Yeah, so Arnab, great talk. What I wanted to understand is this diagram that you showed about the central peak getting quenched, and you know, you have this generation of sidebands. This is exactly what you would see when you pump energy, let's say in an EOM, right? Would you really call this as a cooling, because you are redistributing the energy from the central peak to the higher order sidebands, right? Because cooling would mean you would need to create a dissipative force that takes out energy from the system instead of redistributing the energy into the other modes, right? So would you like to comment on this?
So actually, what our, I mean, the discussion and thoughts. So because like as I said, so it's a like dynamical stable system. So what I mean by that it's not really extracting energy from our system.
Okay.
So it's not really going anywhere.
Okay.
It is there. So as I said earlier, so when we are talking about mechanical modes, each independent harmonic oscillators are like, so each independent, like fundamental mode is a independent harmonic oscillator.
Right.
So that mode is cooled down. I'm not claiming that it will cool down the whole system. So
okay.
In terms of that, you can call that this mode is going down. This
right. So and related question is that you showed us this squeezing graph where you have this quadrature, x and y quadrature plotted. When you do this cooling, do you generate that graph after you have cooled the system, the squeeze graph?
So this graph, when we are doing this, so this graph is not yet like, this is not during the cooling.
Okay.
So this is before that. So this is the earlier work in 2018. So
this is an intrinsic squeezing that happens in the system. Are you saying that?
So this is because of parametric driving.
I see.
This is happening due to parametric driving. Like cooling is not yet there.
I see. Okay. And would you like to say anything about the standard quantum limit? How much is the lowest sensitivity you can go to versus this graph that you've shown here for the system?
That no, I mean, yet I don't have.
Okay, no issue. Fine.
Ashok,
Yeah.
one question.
Yeah. Okay. So
if I could just comment quickly, actually Prasanna and Arijit's question are both the same. And so here actually what Arnab was saying, that it is really another way of looking at it is, this is exactly how refrigeration also works. As long as you have it connected, it will keep low, but there's no center of mass cooling. So only one mode. So if you disconnect the refrigerator, it will just warm up. That's one of the things. And as far as this 3.8 femtometers is concerned, if you actually plug in the 0-point motion and the standard quantum limit, like not the 0-point motion is what you're asking, right? So that would be about like few attometers. So another 3 orders of magnitude, which you could see. Well, SQL is the measurement, right? Like, so that you can have higher, but that's just 1 over square root. Yeah.
Yeah. So you said you can go to like 51 Kelvin. So
Yes.
how far you are from the quantum, the temperature where you start to see the quantum effect?
Yeah, if we look at the phonon occupancy, that will say that we are like well away from the value. The occupancy occupancy is as 10 to the power 10 to the power 6, 7, 8.
No, what I'm saying is let's say probably I might have missed. What is the natural frequency you said?
Its natural frequency is around 2.2 megahertz.
So this is H times 2 is equal to KT. So that temperature would be where you see the quantum effect, let's say, order of magnitude. Now, if you calculate how far you are from 51 Kelvin, so what I'm asking is, like this, you started the experiment from room temperature. Is that actually limiting to 51 Kelvin? Or if you just put in, let's say, liquid nitrogen and initially to start with, you cool it to something like 80 Kelvin or 77 Kelvin, then with same setup, can you even go to that temperature? I mean, that's I'm asking because then you can start seeing the quantum effect directly.
That I need to think about. I don't know.
And we don't understand. Yeah.
There is
the delta T what matters. So we think so, but we don't know. We have not done the experiment.
Okay.
There is actually a linked question on screen. Can one use this cooling method to study diffusion in low temperature quantum domain? From Supurna Sinha. Can you comment on that?
I don't know yet. I mean, I don't know. I cannot say anything.
Okay, great discussion. So, because there is a limitation of time, I think we go to the next talk.
Thank you, everyone.